Copper is a metal of immense importance. It has been vital to human progress for thousands of years. Today, copper's role has expanded dramatically. It is now a cornerstone of modern technology. Our digital lives depend heavily on this reddish-brown metal. From the smallest electronic components to vast power grids, copper is present. It conducts electricity better than almost any other common material. This conductivity makes it indispensable for countless applications. The transition to green energy also relies heavily on copper. Wind turbines, solar panels, and electric vehicles all require significant amounts of copper. As nations strive to reduce their carbon footprint, the demand for copper in these green technologies will only grow. Consider the devices you use every day. Your smartphone, computer, and home wiring all rely on copper. Understanding copper is crucial for appreciating its role in both current technologies and future innovations. Global demand for copper is substantial. Industries consume millions of tons each year. Construction uses copper for wiring, plumbing, and roofing. Electronics drive significant demand. Global refined copper consumption is around 25 million metric tons annually. China fuels vast manufacturing and infrastructure projects. Current consumption pressures global supplies. Developed countries have high per capita consumption. Emerging economies' appetite for copper grows. Demand evolves with economic growth and population increases. The future outlook for copper demand points towards significant growth. Projections suggest that by 2030 or 2040, annual copper demand could increase substantially. This anticipated surge is largely driven by the global transition towards cleaner energy systems. The shift to electric vehicles is a primary factor, with EVs using about 3 to 4 times more copper than conventional cars. Renewable energy installations are another major driver of future copper demand. Solar photovoltaic systems and wind turbines require large amounts of copper for their components. As countries accelerate their renewable energy deployments to meet climate targets, the demand for copper from this sector will escalate dramatically. Beyond electric vehicles and renewables, continued global development will also contribute to rising copper consumption. Urbanization in developing countries means more buildings, power lines, and appliances, all of which require copper. The expansion of telecommunications networks, including 5G infrastructure, will also add to the demand. Therefore, the projections for future copper needs are based on clear trends and stated policy goals from governments worldwide. While the Earth holds substantial copper reserves, accessing them presents growing challenges. Global copper reserves are estimated to be around 870 million metric tons. Identified resources are even larger, potentially exceeding 5 billion metric tons. However, the issue is not just the total amount of copper in the ground, it is the quality of the ore and the ease of extraction. Over many decades of mining, the richest and most easily accessible copper deposits have been largely depleted. A significant challenge facing the copper mining industry is the steady decline in average ore grades. Today, the average grade at many mines is below 1%, and in some cases significantly lower. This means that much more rock must be mined, transported, crushed, and processed to extract the same amount of copper. This directly translates to higher energy consumption, increased water usage, and greater waste rock production per unit of copper produced. Mining operations are also increasingly moving to more remote and challenging locations. As easily accessible deposits are exhausted, companies must explore in geographically difficult terrains or politically unstable regions. The combination of declining ore grades and more difficult mining conditions puts significant pressure on the supply chain. These inherent challenges in the physical act of extracting copper from the earth are central to the question of whether supply can keep pace with future needs. Global development aspirations are inextricably linked with increased copper consumption. As nations strive to improve living standards for their citizens, they invest in infrastructure. This includes building new cities, expanding transportation networks, and ensuring access to electricity and clean water. All these development activities require vast quantities of copper. The global push towards renewable energy further amplifies this demand. Ambitious targets for solar and wind power generation set by numerous countries translate directly into a greater need for copper. A typical onshore wind turbine can contain several tons of copper, primarily in its generator and cables. Similarly, large-scale solar farms utilize considerable amounts of copper in their cabling, inverters, and transformers. Electric vehicles represent another critical component of this increased demand. an electric car contains significantly more copper than its internal combustion engine counterpart. Furthermore, the rollout of EV charging infrastructure also requires substantial copper for cables and components. Therefore, the combined forces of general global development and the targeted shift towards renewable energy and electric mobility create a powerful surge in copper demand. Copper mining, while essential for modern life and green technologies, carries significant environmental and social burdens. Large open-pit mines involve removing vast quantities of overlying rock and soil, altering landscapes and destroying habitats. The waste rock, known as tailings, must be stored in large impoundments, posing risks if not managed properly. Water usage is another major environmental concern associated with copper mining. Processing copper ore requires substantial amounts of water, straining local water resources in arid regions. Mining activities can lead to water pollution through acid mine drainage. The social implications of copper mining can also be profound, particularly in key producing countries. Ensuring that mining operations respect human rights, engage transparently with local populations, and contribute positively to local development is a constant challenge. The global demand for copper means that these local impacts have global relevance, highlighting the need for responsible sourcing practices throughout the supply chain. Technological innovation in mining and processing offers a pathway to mitigate some of the challenges in copper supply. New exploration technologies can help locate deeper or more complex ore bodies with greater precision. In extraction, innovations like automated drilling and hauling systems can improve efficiency and safety. More importantly, advancements in mineral processing can enable the economic extraction of copper from lower-grade ores with potentially reduced environmental impact. Recycling, often termed urban mining, plays an increasingly vital role in meeting copper demand and reducing the need for new mining. Copper is highly recyclable. It can be recycled repeatedly without any loss of its inherent properties. Enhancing collection systems, improving sorting technologies, and designing products for easier disassembly can significantly boost copper recycling rates globally. The potential for increased copper recycling is substantial. Developing efficient and economically viable processes to recover copper from complex products is a key area for innovation. Investing in research and development for these technological solutions and recycling infrastructure is crucial. While copper possesses an exceptional combination of properties, the possibility of using substitute materials in certain applications is an important consideration. For electrical conductivity, silver is superior, but its high cost makes it impractical for widespread use. Aluminum is a more viable competitor, already used in some high-voltage overhead power transmission lines. However, aluminum has lower conductivity than copper, meaning larger conductor sizes are needed for the same current carrying capacity. In other areas, such as plumbing, plastics like PEX have made inroads as substitutes for copper pipes. Fiber optic cables have replaced copper in many long-distance telecommunication applications. However, for many core applications, copper's unique combination of properties makes it very difficult to replace without significant performance compromises or increased costs. The search for effective substitutes is ongoing, driven by price fluctuations and supply concerns. The challenge of ensuring a sufficient and sustainable copper supply for global development is complex. It requires a multifaceted approach that balances economic needs with environmental protection and social equity. Successfully navigating this challenge necessitates global cooperation. Producing countries, consuming nations, mining companies, manufacturers, and research institutions must work together. This collaboration should focus on developing and deploying innovative mining and processing technologies that reduce environmental footprints. It must also prioritize the expansion of copper recycling infrastructure worldwide. Sharing best practices in sustainable mining, ensuring fair benefit sharing with local communities, and upholding stringent environmental standards globally are all part of this cooperative effort. International forums and agreements can facilitate this dialogue and action. Ultimately, the goal is to achieve a sustainable balance. We need copper for progress, but that progress cannot come at an unacceptable cost to the planet or its people. The path forward involves innovation, responsibility, and a shared commitment to a sustainable future. By fostering global cooperation and embracing sustainable solutions, we can ensure that copper continues to be a force for positive change, powering a prosperous and environmentally sound future for all.